Hi guys, so today we're going to be going over your lab, which is going to be reporting, modeling geometry and polarity on our Labflow. So let's go ahead and get started. So for the first part, we're going to go over macroscopic versus microscopic, right? Macroscopic are the things that we can see with our eyes. Sometimes we do need a little bit of help from a microscope to be able to see these, but we could still see them. So here on this first part, it's just the process of observation. You want to record 2 to 3 physical properties that you observe from these molecules. All right, so we have sodium chloride, table sugar, iodine crystals, and sulfur. Now, if I look at sodium chloride, I could see that it is white, right? You guys can see that it has like white. It's a bit whitish clear, actually, so clear white. So I'm going to write clear white. And the other things I noticed is that these are all little cubes, right? Look at that. They form little cubes. Here's one side, another, two. So it's cubed shaped. And the other thing I noticed is that they're all cubes, right? They're not perfect cubes, but they're still cubes. And I don't notice any like tiny little breakage. Like I see here, I see little breakages everywhere on this one, but I don't see that on this one. So that tells me that it's not as brittle, so not brittle. Okay, and this is for sodium chloride. Now, these are my 3 observations that I noticed for sodium chloride. You're going to write yours as well for the rest of them, and what are your observations. And you're going to put it here under your physical characteristics, okay? Now, it also tells us the type of molecule, so it doesn't have us guess. It tells us that sodium chloride is ionic, sucrose, which is sugar, is polar, iodine is nonpolar, and sulfur is nonpolar. All right, so now knowing this information, we're going to go ahead and move on. It says we're going to look now at a microscopic view of sodium chloride. So microscopic is a view that we cannot actually see, so we need computers to actually help generate the images. In this one, it's sodium chloride, right, NaCl, and what we want you to do is describe what you're noticing, right? So in this lattice, ionic compounds form lattices. So this is a lattice. There's that word again. Okay. We could see that we have a 1-to-1 ratio, right? 1 purple to 1 green. Cations, which are your positive ions, they're actually bigger than anions. So in this case, we have, it's going to be your sodium, chlorine, sodium, chlorine, sodium, chlorine, and it's connected all the way through making sodium chlorine. Now, I want you to describe this to me, right? What is the ratio of sodium to chlorine? What kind of structure does it make? What was that keyword? And what is the shape that it forms? The shape that it forms, okay? Is it organized or disorganized? So organized or disorganized, right? So answer those questions right here for your microscopic view. So this is for your microscopic. All right, let's go ahead now and move on to the next part after we give our observation. We're going to talk about polarity demonstrations right here. And in this video, in this part right here, the polarity demonstrations, you have 1, 2, 3, 4, 5 different vials. This one is going to be your base vial, right? And it's made with water and oil. All of them have water and oil inside of them. Yet in these ones, we added our different compounds: iodine, copper sulfate, sulfur, and sodium chloride. And we noticed that something different happens. So the first thing we want to see is we want to use this as our base, right? This is our background. And see what happened when we add. So if I describe the one where we add iodine, right? So here we go. Here's my H2O, and in this one is my iodine now. The iodine, it mixed with the oil. Okay, so the iodine mixed with the oil. what does that tell us? Well, oil has large hydrocarbons. Okay, so it has large hydrocarbon groups, right? And it mixed with this, not with the H2O. H2O is a polar molecule. H2O is a polar molecule. That tells me that my oil with large hydrocarbons is going to be nonpolar. And if oil is nonpolar and the iodine mixed with the oil, therefore the iodine is also going to be a nonpolar molecule. Why? Because like dissolves like. Like dissolves like. So that means polar dissolves polar, and vice versa with nonpolar dissolves nonpolar. So you want to describe that the iodine mixed with the oil, and this was evident by the purplish color in the oil, and the water was still clear. You also had your purple crystals of iodine inside the water, which indicate that the iodine is not dissolving in the water. It's not dissolving in the water. Okay. And you can see the difference between these other ones where copper sulfate did dissolve inside of the water. All right, so you want to go ahead and write those observations down on what you notice on each of the layers for water and oil for sodium chloride, sulfur, iodine, and copper. All right, now we want to classify them as polar or nonpolar. We were looking at the one with iodine, and we said iodine mixed with oil. And it mixed with oil, knowing that oil is nonpolar, iodine will also be nonpolar. So we would just choose nonpolar. Moving on to the next part. This part of the lab, you're going to actually have to print out or write down everything on a page and submit this. Okay, it's a huge chunk of the points, so 18 points in this section and on the rest of them. So make sure you submit your work. So it says draw the Lewis structures for each of the following molecules or ions. And then you're going to upload your image here. So if you want to open up the lab, the PDF to look at it, let's go ahead and find it. It's going to look like this right here. So part C, covalent compounds. This is the part that we're going to fill in. So I'm going to go ahead and do one of these with you guys so we could just get all the information we need. So I will go ahead and do methane because it's the first one. All right. The first thing it wants to know is valence electrons. So how many valence electrons are present? Right. So carbon has, what does carbon have? Carbon has 4 valence electrons. Hydrogen has 1 valence electrons, and there's 4 of those, so that's 4. If we add these together, that's going to be 8 valence electrons total. The number of electron pairs. Okay, so the number of electron pairs, so we have to actually draw the molecule in order to figure out how many electron pairs there is. So unbonded pairs is most likely it. So I'm going to have carbon. Carbon can make up to 4 bonds, and there is exactly 4 hydrogens. So as I place this is 2, 4, 6, 8 electrons full and completely move through. So there is 0 lone pairs and there is 4 steric pairs. I really am not quite sure which one it's asking for, but I'm pretty sure it's asking for if there's any lone pairs. And in this case, there's 0 electron pairs, right? If not, go ahead. So I would say 0, since we're handwriting it anyways. So 0 lone pairs. This is what I want you guys to do then. And 4 steric. So steric just means connections, connected together. So that's 1, 2, 3, 4. So 4 steric or 4 bonded pairs. All right. If we were to look at another one, let's just do another one because I don't want you guys to be confused or anything like that. Let's look H3. Okay, so nitrogen has 5 valence electrons, and each hydrogen has 1, and there's 3, so that gives me a total of 8 valence electrons. So I would have valence electrons equal to 8. I'm going to go ahead and draw this. So I have nitrogen, it's connected to 3 hydrogens, 1, 2, 3, and I have 8 electrons, 2, 4, 6, 8, right there. So this one, and we noticed that NH3, it's ammonia, so it actually has a positive charge to it. It's not showing it on here, but it actually has a positive charge. So I'm going to leave it as this, and now we're going to go ahead and count. So lone pairs is equal to 1. We have 1 lone pair. And for the number of bonds, so electron pair bonded, or my steric, I'm going to say 3 steric, or 3 bonded. Right? Steric, just one more time, means connected to the center. How many points do you have connected to that center? All right, so this is what we mean about that part. Once you're done, go ahead and submit it here. All right, now we're going to move on and see the next part. So the next part says obtain a molecular model kit, and then we're going to build the molecules, right? So geometry sets, part 1. And do we have to submit this? Yes. Okay. So now we're going to fill in this steric section, and we're actually going to draw other molecules as well. So as we fill in the steric section, it's going to be based on the drawings we just made, right? So based on these drawings, for CH4, this one that we said it had 4 steric. The electron geometry is the shape that it formed, and it's 1, 2, 3, 4. It formed the tetrahedral. The number of bonding electron groups is 4. The number of lone pairs, 0. The molecular geometry is also a tetrahedral, and that is because there is no lone pairs. Lone pairs would actually make it a different shape. How many bonds have a dipole? 0. So here, hydrogen is not very electronegative. It only has 1 electron to go around. There is no charges in this molecule. So this is a non-polar molecule. It's also a hydrocarbon, and hydrocarbons, which is carbon and hydrogen, tend to be non-polar, especially the bigger they get. So this is a non-polar molecule, and it doesn't have any dipoles. Dipoles is when you have an actual charge. Like for example, here nitrogen has a slightly positive dipole. So 0 dipoles. If present, do the dipoles cancel each other? Not available because there is no dipoles. Is this molecule polar? No. Now let's look at NH3 just because we already did NH3 here. How many sterics does it have? It has 3. What is the electron geometry? Well, the electron geometry, if we remember, it includes the electrons on here. So according to the electron geometry, we have this shape right here, which is a tetrahedral. The number of bonding electrons, though, is 3. The number of lone pairs is 1. So that actually is going to change the molecular geometry, because the molecular geometry does not count the electrons as a group. So now instead we have this shape here, which is going to be a trigonal pyramidal. Okay. Go ahead and review your notes when we did electron geometry, I believe in chapter 9. So how many bonds have a dipole? In this case, this 1 bond has a dipole. So we're going to write 1 has a dipole. If present, do the dipoles cancel each other out? No, they do not cancel each other out. Now, if this is slightly positive, there is going to be somewhere where there's going to be slightly negative. And remember, the best way to actually figure that out is by taking the formal charge of it. But we don't need to get that technical. Is this molecule polar? Well, in order to figure out if something's polar or non-polar without having to do the whole formal charges and whatnot, just look if it's symmetrical or not symmetrical. And here, although the shape might look like it's symmetrical, this electron shape, we have a positive dipole up here, right? So that means the electrons are pulling elsewhere, okay? And because of that, the symmetry here is not the same. So we have the electron cloud looking more like this as opposed to something more evened out like that. Okay, so it's asymmetric, which means it's going to be a polar molecule. The charges are asymmetric. All right, so hopefully that helped you guys out with this section. And now you're going to repeat the same thing, but now you're going to be using different types of molecules. So you're going to be using ions now when doing this. So group 2 compounds and ions, you're going to draw them out again, and you're going to do the same exact steps we just did. Okay. Molecules with multiple central atoms. So when you have molecules with multiple central atoms, you want to try to build them. Let's see what it says. Choose one compound from below to build. Record the molecular formula on your worksheet. After you build it, sketch its shape on the report sheet using the line dash wedge. Okay, so let's look at this worksheet. It wants us to do this part right here. Okay, so remember, you're going to be turning all of this in. So when you submit it, if you have to submit the same sheet, so like this sheet right here is also one of the ones that goes here, just submit it again, right? Don't just assume that you submitted it once, put it in every part. All right, so the molecule name and whatnot. I did submit a video on naming, okay, and I'll try to attach it at the end of this Labflow as well, so that way they can be connected on how to name these. All right, so let's go ahead and do this one. 1, 2, 3, 4. It has 4. 1, 2, 3, 4 carbons. And in it, this one's a double bond, single, single, and then the rest of these are hydrogens. 2, 3, 4, 1, 2. All right. So it looks something like this. Or is that a triple bond? That might be a triple bond. Actually, can't tell. Let me zoom in. Okay, yeah, it's a triple bond. That is hard to see. So it's a triple bond, which means there's only one hydrogen. Okay, so now that we have our molecule, it wants us to build it. So you just want to build the stick figure. It's called the ball and stick figure. So you're going to have your carbons, and attached to each one of your carbons is going to be your hydrogens, which are these tiny little ones right here. And this is going to look like this. Okay, so you're going to draw a ball and stick figure. So this is the first one. You'll notice that this doesn't really have that representation, although it can, because this should actually been shorter. Should be shorter. Okay. So whenever you have these, just make sure it's a ball and stick figure and you're representing them. A single bond is larger, a double bond is shorter than the single, and the triple bond is the shortest and the strongest bond. So you could actually represent those by putting them on here, right? Via length. Okay. Now it wants us to name these. Like I said, I made a video on naming, so I'll just quickly kind of go through it. This right here has 4 carbons, so it's a butane base. And in this butane base, we have a triple bond right here. A triple bond is known as an alkyne. So it's an alkyne group with the butane base. So when I name this, I'm going to actually be combining this. And I'm going to drop the ane because ane is for an alkane, which is a single bond. And I'm going to call this butane. So this is a butane group. All right, so really quickly with namings, you have alkanes, which are single bonds, alkenes, which are double, and alkynes, which are triple bonds. Okay, so those right there are the formulations of our base, and this is what we name them, the last of it. And then the but part is part of the roots. So the root system, the root words, we have meth, and we have F, prop, and but, and it goes on and on and on. It's actually in the other video that I made. So in this case, we have 4 carbons, so that would be but. Okay, and then we'll say butane, right? Because it ends in "ine." So you'll just put this as your suffix, the "ine." Now, okay, well, we're gonna leave it at that. That's the simple one. Like I said, continue watching after this for more information. Okay, post-lab questions. It wants you, in this case, to name different groups that you might see. It wants you to name the shapes of the groups. So here you see this carbon has a tetrahedral shape. So now it wants you to find a different shape and name that different shape. Okay, so you're going to have a different shape here, right, from this carbon right here. So you'll draw this out basically and then name more shapes that you're going to find here. Like here's a different shape. What shape is this? Is it linear? Is it bent? Okay, you figure it out, right? Download your stuff and then you're good. And then, yep, the rest is for structural formulas. All right, you guys, I hope the video helps, right? And stay tuned. It's connected to this. It's the other video. Actually, I'll just add it as on the YouTube, the little part at the end of it. All right, you guys, take care.